Hello everyone, welcome to the 10th lecture of Module 1 in the course Information and Communication Theory. Here we are going to discuss conditional distribution and conditional expected values. Till now we have discussed conditional probability in one of the previous lecture, and actually this conditional distribution can be derived or can be obtained from conditional probabilities. Let us consider the CDF of this conditional event Z over M. Z over M represents that we are calculating the probability of event Z provided that event M is already happened. So this CDF of conditional event Z over M is actually given as probability of random variable Z less than equals to this value Z provided that event M is already happened. So this is the reason why it is called as conditional probability and conditional distribution. By using Bayes theorem, we can easily write this probability as probability of intersection of the events Z less than equals to Z and second event M divided by probability of event M. Similarly, if we have two random variables Z and W and both are depending over a third event M. So here if we write FZW of ZW over M, it actually means that we want to calculate probability of intersection of the events Z less than Z and W less than equals to W provided that event M is already happened. So if we again use Bayes theorem, this conditional probability can be written as probability of intersection of the events Z less than equals to Z, W less than equals to W and third event M. So this numerator is the probability of intersection of these three events over probability of event M. So in this manner we can easily define conditional distribution for one random variable Z or conditional distribution for conditional joint distribution for two random variable Z and W. Now in this definition, let us consider that event M is defined as X less than equals to X. So for this, if we substitute this equation of M in this conditional distribution, then we get, and we are considering Z equals to Y, then we will get f of y by M, which is now given as X less than equals to X. Means here we are actually determining probability of the event Y less than equals to Y such that event X less than equals to X is already happened. And this further, if we use Bayes theorem, can be written as probability of intersection of the events Y less than equals to Y and X less than equals to X divided by probability of the event X less than equals to X, or the numerator is equals to joint distribution function of random variable xy, that is capital F xy of xy, over the CDF of random variable x, that is fxx. So this conditional distribution function can easily be obtained by considering the joint distribution function of the two random variable over or divided by the CDF of one of the random variable, and the CDF of random variable that will be used in denominator will be what will be the event that will happen before, that is the event M. So similarly, in same manner we can define the conditional density function, which is given as small fy y over x less than equals to x, and this is nothing but the derivative of this conditional distribution function with respect to the random variable y. So this will be equals to del by del y of this whole quantity, but since only numerator is depending on random variable y, denominator is independent, so we can write it as del of del y of fxy xy over simply the CDF of x. Now let us consider a second scenario where the event m is defined like this one, that event m is actually the random variable assigned to the events for which the values assigned will be in between x1 and x2 with x2 included. For this case of event m, if we want to define the conditional joint distribution, that is fxy xy by x1 less than x less than equals to x2, and it automatically means that we are actually calculating probability of event x less than equals to x and y less than equals to y, or it is we are calculating probability of intersection of these two events provided this event x1 less than x less than equals to x2 is already happened. So if we again use the Bayes theorem, we will get the numerator as probability of the intersection of three events. First two events are the same, x less than equals to x, y less than equals to y, while third event is this one, that is x1 less than x less than equals to x2. So numerator is probability of x less than x, y less than y, x between x1 x2, divided by denominator is the probability of this event, that is x1 less than x less than x2. Now if we further elaborate this, we can say that the values of x and the values of x1 x2, all the three values lie along the x-axis. So we get three possibilities. First possibility is the value of x is less than x1, that is the value of x is falling outside of this interval. In that scenario, the intersection of this event and this event will be null set. It means probability of null set equals to 0, means numerator quantity will become 0, so the overall conditional joint distribution becomes 0 for x less than equals to x1. Now consider that the value x lies within the range x1 to x2. So now we have this point, let us say this is x1, this point is x2. So the range x1 x2 is starting from here, goes up to here, and we are assuming that x value lies somewhere in between these two values, and let us consider it is lying here. So we again need to consider out or find out what may be the intersection of this event with this event. So the intersection of this event with this event will be this range. So we can say that the numerator will become fxy xy minus fxy x1y, because the probability x or y less than equals to y along with x1 less than x less than equals to x2, this we have already discussed in conditional probability. This will be equals to f of this higher value x2 with y minus f of this lower value x1 y. So by using this formula of conditional probability, since the intersection of this event along with this event is x1 to x and third event y less than equals to y is already there, so the probability defined in numerator will actually equals to fxy minus fx1y, and denominator will be fxx2 minus fxx1 because it is really depending on one random variable. So for x1 to x2 we will get this as the value of fxy xy over m. Now consider the third case when x falls outside of this region such that x is greater than x2. Till now we have discussed x less than x1 means x falls somewhere here. Second case when x1 is in between x1 and x2, and third case x is greater than x2. In that case, if x is greater than x2 means x lies here, then the intersection of this interval along with this whole interval is same x1 to x2. So denominator will be same fx2 minus fx1, but numerator now will be fx2y minus fx1y. So numerator will be fx2y minus fx1y divided by fx2 minus fx1. So in this manner, whatever may be the event m defined either in terms of random variable x or random variable y, we can easily determine this conditional joint distribution. Now we have the expression of distribution function. From this we can derive the expression of density function. For getting expression of density function, it involves two random variable, so we need to differentiate distribution function twice, first with respect to random variable x, second with respect to random variable y. Or we can say we should differentiate this distribution function with respect to del x and del y. But just see here, this distribution function contains three components. The first component is 0, so there is no need of differentiating this component. Second component, if you see, both numerator and denominator are independent of random variable x, means with respect to y it will be differentiate out, but with respect to x it will be treated as constant. So finally if you differentiate to get the density function, it comes out as 0. It means non-zero density function will exist only for this range of random variable x. That's why we are defining the density function only for this range, and that will be equals to del square by del x del y of this function. But this function numerator again contains two components. One is depending on random variable x, but other is independent of random variable x. It means the after differentiation we will get only the differentiation corresponding to this component. So if you differentiate fxy xy with respect to del x and del y, we will get numerator as the density function is small fxy xy, and denominator will be same fx2 minus fx1. So in this manner we can easily determine both distribution function and density function for conditional distribution. Let us consider one example. In this case the fxy is given as k for the range 0 less than x less than y, and density function equals to 0 otherwise, means if x y is not satisfying this relation then the density function is 0. And we have been asked to find out what may be the conditional distribution fx by y and fy by x. For this let us consider the first we need to determine what will be the value of the k. For this first consider this figure. Here this line will represent y equals to x. Below this line it represent x greater than y. Above this line represent x less than y. So within the condition we have given as x less than y, means we are interested only to the region above this line. Second thing, both x and y are defined only in between 0 and 1. So along x-axis we have drawn the graph for 0 to 1. Along y-axis we have also drawn the graph from 0 to 1. Means only this shaded region will represented by this condition. So this is the reason why we are using this graph to get out the conditional distribution. Now we have already know whatever may be the density function, either conditional or whatever, if we integrate it for entire region, it results out as unity. So double integral of fxy dx dy will equals to 1, and double integral, because this density function is depending on two random variables, so it will be integrated with respect to both the random variable. This will be equals to fxy xy dx dy. Dx is allowed to vary 0 to y, or x is allowed to vary from 0 to y, and y is allowed to vary from 0 to 1. Let us consider this point. At this point, the value of x equals to y. It means if we consider y is allowed to vary between 0 to 1, then at whatever value the y is residing in between 0 to 1, at that point the value of x is only vary up to 0 to y. This is the reason why the limits of integration with respect to x is considered as 0 to y, and with respect to y it is considered as 0 to 1. And if we solve it, we will get k by 2, which is equals to 1. It automatically means the value of k must be equals to 2. So for this case, the fxx, that is the CDF of random variable x, will be integration of this joint PDF or joint density function with respect to random variable y, because we want only the density function in terms of x, so we need to integrate out any y dependency. So fxy will be integrated with respect to y variable. For the limit of y is starting from x goes up to 1. So for the limit x to 1, and if you integrate it, you will get k into 1 minus x, and it is defined for the range x 0 to 1. Similarly, if one wish to find out the CDF of random variable y, it means we need to integrate this joint density function with respect to x to remove x dependency, and the limit of integration is, since we are integrating with respect to x, so limit of integration is from 0 to y. So if we integrate it from 0 to y, you will get the final expression as equals to ky, and this is again valid for y ranging from 0 to 1. Now we can easily determine the fxy, because fxy by formula is equals to joint density function divided by PDF of random variable y, that is fxy divided by fy. Fxy is for this range 0 to x to y to 1 is already defined as k, and fyy or fy is defined as ky, so k divided by ky is 1 by y. Similarly, we can determine the conditional density function of random variable y provided x is already happened. In that case, it is equals to joint density function divided by PDF of random variable x, that is equals to 1 by 1 minus x, because k by k will cancel out, so we will get 1 by 1 minus x for the range 0 to x to less y to y 1. So in that manner, one can easily define the conditional density function which is derived by using Bayes' theorem from joint density function and individual density functions. Next, if we are moving to conditional expected value. Conditional expected value, by using this theorem, that expectation of gx, any function of a random variable x, is integration gx fx x dx, that is the PDF of random variable x. This formula is used to obtain conditional density. Let us say we want to find out conditional density, that is expectation of gy over m. It automatically means we are actually wanting to evaluate the integration of gy multiplied by fy by m dy. So conditional mean of y will equals to expectation of y provided x already happened. Conditional mean of y, if you only calculate mean of y, that will be equals to expectation of y. But conditional mean of y is expectation of y provided that a event already happened on which the event y is depending. So if this is represented as neta y by x, it will be equals to integration y conditional density function of y over x by using this formula. So this will be the conditional mean of y. In a similar manner, we can define conditional variance of y, that will be represented as sigma y by x whole square, and it will be equals to expectation of y minus conditional mean of y by x whole square slash x. It actually represent expectation of the event y minus neta y by x whole square provided event x already happened. This will, again by using this formula, will be equals to this function y minus neta y by x whole square multiplied by the conditional density function of fy by x and integration with respect to y from minus infinity to infinity. So all these formula we are again going to utilize in solving this example. Let us consider that joint density function fxy is given as 1 for now this range 0 less than magnitude y less than x less than 1 and otherwise 0, and we have been asked to determine ex by y and ey by x. For this, since here is magnitude y which is less than x, it means if we consider this line as x equals to y, then the region below this line will represent y less than x, and since here is magnitude, so we need to consider both positive and negative side. So this condition will actually be represented by this shaded region where x is maximally allowed to vary between 0 to 1 and y is maximally allowed to vary between -1 to +1. Now for this reason we need to determine the conditional expectation value ex over y and ey over x. Now the joint PDF for this region equals to 1. So we can easily determine first the respective individual PDFs of random variable x and y. So PDF of random variable x will be equals to integration of joint density function with respect to y. Here if you want to get the PDF x, we need to integrate with respect to y such as to remove the y dependency in this joint density function, and y has to, or the component of y has to integrate out for the range of y starting from -x to +x. It means if you consider this line, then this will be -x to +x, and if you solve it within this limit, the joint density function will equals to 1. So if you solve it, you will get it as 2x for the range 0 to x to 1. Similarly, The PDF of random variable y will be the integration of joint density function with respect to x variable, and x is allowed to vary between magnitude y to 1, and if you integrate you will get this quantity as 1 minus magnitude y for 0 to y to 1. These two PDFs will be utilized to first calculate the conditional density function. So the conditional density function fx by y will equals to joint density function divided by PDF of y, that is fy. So joint density function is 1 for this range, so you will get 1 by 1 minus y for this range of y and x. Similarly, the conditional density function fy by x will be equals to joint density function divided by PDF of x, that is equals to 1 divided by 2x for again this range 0 to magnitude 0 less than magnitude y less than x less than 1. Now these two conditional density function will be used to determine ex by y and ey by x. We have just got the conditional density function fx by y as 1 by 1 minus magnitude y and fy by x as 1 by 2x, and if we utilize it in the expression of expectation of event x provided event y already happened, that will be integration x multiplied by conditional density function fx by y. So if you substitute this, you will get x divided by 1 by magnitude y, this integration with respect to variable x, and the range of x will be from magnitude y to 1, and if you solve you will get this expectation value as 1 plus magnitude y by 2. Similarly, if one wants to calculate expectation of y over x, that is it is actually equals to probability of the event y such that event x already happened, that will be integration of numerator quantity y multiplied by conditional density of y by x with respect to variable y whatever is here, and since we are integrating with respect to variable y, so the variable y which is defined as magnitude y less than x within that region, so we need to actually integrate it from y equals to minus x to y equals to plus x. So if you integrate you will get it as 0. So the expectation of x over y we are getting as 1 plus magnitude y by 2, expectation of y over x we are getting as 0. Whatever we have discussed in this lecture you can easily found in this book, Papolis, Probability, Random Variable and Stochastic Process, 3rd edition. Thank you.